Hello everyone. So let's now solve practice assignment week 8, question number 1. An inner product on R3 is defined as, this is nothing but our usual dot product, match a set S in column A with the set T in column B so that T belongs to span of S or so this means every element in the set T would be orthogonal to the set S. Match a set in column B with the property satisfied in column C. Let's look at each element one by one. So from the column A, if we look at the first set, so consider it as set SA, which is this minus 2 comma 1 comma 3. So if you find the orthogonal complement, it would be all x, y, z in R3 such that inner product with minus 2 comma 1 comma 3 would be 0. So if we it would be minus 2x plus y plus 3z is equal to 0. Now all we need to do is check which of the following sets in column B satisfy this condition, that is minus 2x plus y plus 3z equal to 0. So our condition is minus 2x plus y plus 3z is equal to 0. So let's check for this condition. If we check the first element 0, 1, 1, it is x value 0, y value 1, z value 2 be 0. So this would result in 4. So that means this is not satisfied. So this set is not in the orthogonal complement for this set. Now let's look at this set. Now here 1 minus 1 1. So if we put 1 minus 1 1 here, we get minus 2 minus 1 plus 3, and that is equal to 0. So for this vector it is satisfied. Now for the second vector, this condition would become minus 4 plus 1 plus 3, and this is also 0. So both of the vectors satisfy this condition, and we also know the dimension of the set, dimension of this set is nothing but 2. So you get only 2 vectors. So this set belongs to the orthogonal complement for this set. So A will match with 2. So if we look at the option, this fifth option only where A is matching with 2, but now here it is also saying that it should match with 3. So that means not orthogonal match. That means these two vectors are not orthogonal to each other. So let's see if they are orthogonal to each other, their dot product should be 0. So if we check the dot product, it would be 2 minus 1 plus 1, and that is not equal to 0. So these vectors are not orthogonal to each other. So this is the correct relation. So fifth option is correct. Similarly, we will check for the other option. Now, if we want, we can check in this way, but let's now go with the help of options. We will check now. So for the B, there's only one option here which says B will match with the fourth option. So if you look at the B vector, that means this vector is orthogonal complement for this set. So if we take the orthogonal, if we take the dot product of this vector with the vector 1, 1, 1, so that is 1, minus 2, 1 with 1, 1, 1, that would result in 1 minus 2 plus 1, and that is 0. So for the first vector, it is okay. Now let's check for the second vector 1 minus 2 1, and that is with minus 1 0 1, and we get minus 1 plus 1, and that is also 0. So for both the vector it is satisfied, and that means this set is orthogonal complement for this set. Now but in the option next it says is 4 will match with 2, so that is orthogonal but not orthonormal. That means these vectors are not orthonormal, but we can see these vectors are normalized, as the norm of this vector would be 3 root 3, so it is dividing by the norm, so it is normalized, and norm of this vector would be root 2, so this is also normalized as we are dividing it by root 2. So these vectors are orthonormal, and we can also see that they are orthogonal also, as the dot product of these two vectors would be minus 1 plus 0 plus 1, that is 0. So they are orthogonal also or orthonormal. So that means it will not match with this. So that's why this option is incorrect, as our vectors are orthonormal too. Now if we check for the C, again there's only one option for the C, that is C will match with 2. But we have already seen that C is matching with, sorry, A is matching with 2, but still let's just confirm it once again. So our vector in the C is 1, 1, minus 1. And if we take the inner product of this vector with the vector 1, minus 1, 1, we'll get 1, minus 1, minus 1, and that is not equal to 0. So that means the vectors are not orthogonal to each other. So this is not the correct matching. That's why this option is wrong. And for the A option, we have already checked, so it is already wrong. Now we are left with only for the D. So D will either match with 2 or 3. So for the D, we have the vector 0, 1, 1 and 1, 1, 1. So we have already seen that B is matching with the fourth. So that means D should match with the third or second. Oh, sorry, we have to check with the second and third. So as it is already clear that the second uh, is matching with the A, so of course B cannot match with this. So it's pretty clear, but still let's just confirm it once again. So let's take the dot product of 0, 1, 1 and 1 minus 1. 0, 1, 1 and 1 minus 1, 1. So if we take the dot product, it will be minus 1 plus 1, 0. Okay, for this it is satisfied. Now let's check for the other second vector. It is 0, 1, 1 and 2, 1, 1. So this would be 1 plus 1, that is not equal to 0. So it is not satisfied. And anyway, we have already seen that the second one is matching with the A. So this would not match with D. So the only be left with third. So it should match with third. But let's check it. So 0, 1, 1 and 0 minus 1, 1. So if we take that dot product, it would be minus 1 plus 1, 0. So it is okay. Now for the second vector, it is 1, 1, 1 and 0 minus 1, 1. So it would be minus 1 plus 1, that is also 0. So it is satisfied for both the vector. So D will match with third. And according to the option, it should also match with fourth. So the fourth option tells orthonormal. So it is already normalized, okay, but does not form a basis of a vector space which is isomorphic to R2. So clearly this set is a one-dimensional space. That is the dimension of this set. The dimension of the spanning set for this set would be 1, and we want to find that whether the vector space that is formed by the spanning set for this would be isomorphic to R2. So uh, first of all, if this is, I have already seen in linear transformation case that if we have a transformation from V to W, so V and W are said to be isomorphic when there exists one transformation between V and W, which is isomorphism transformation. But we know that for the isomorphism to be exist, the dimension of V and W should be equal. Only that is the case when the isomorphism case exists, that is when our transformation would be 1 to 1 and on to. In all the remaining two cases, that is when dimension of V is greater than dimension of W or dimension of W is greater than dimension of V, it would not be 1 to 1 in one case, that is when dimension of V is greater than W, and it will not be on to when dimension of W is greater than dimension of V. This is we have already seen in week 5 tutorial. So we can, if you can revisit that tutorial video if you have forgot about it. So for the isomorphism to exist, that dimension should be same. but here dimension would be 1 while dimension of R2 is 2. So there is no there is no transformation exists between R2 and the vector space spanned by this, that is isomorphic. So this option, so this matching is correct. So that's why the second option is also correct. Thank you.